Yeah. So it's extremely grateful to you for agreeing to give this talk on the third Krishnanunni Memorial Lecture. And I would also like to welcome all my colleagues and especially uh, Dr. Krishnanunni's sisters and his other relatives to participate, and also Dr. Shridhamurthy, who is going to chair this today's session. So I welcome you all, and as you all know that this, in the memory of Dr. Krishnanunni, this lecture series we have started, and this is the third in the series, and very eminent people from all over the world who knows Krishnanunni very well have agreed to come and deliver this talk. And today's, I think the talk is very important about the fragmentation of the Gondwana, and I think one of the software which has been written is instrumental, Professor Colin Reeves, which he has used to do. So I think we are going to have extremely uh, novel and different ideas on this, how this all happened. And especially, I recall Rasik would remember when we set up our second station in Antarctica, the idea was, it is on the east side of the Antarctica. An idea was to take up the study on the fragmentation. And I think this problem is still very much alive. And I think it would be extremely useful for us to get the knowledge from Professor Reeves, who is one of the topmost exploration geophysicists in the world. And we are extremely grateful for his agreeing to. With this few words, I again welcome you all, and I request Professor Shridhamurthy to chair the session and introduce the speaker.
Mr. President, I agree
Yes.
to introduce, but the chairing the session is your job, but I will definitely be your
No,
assistant during.
No.
President of the
You
meeting,
can't
Dr.
overrule President. You can't overrule President.
President of the meeting, Dr. Shailesh Nayak. Speaker of the day, Professor Colin Reeves. Family members of Revered Shri Krishnanunni Garu and friends. It is a pleasure and privilege for me to formally introduce Professor Colin Reeves to these video attendees, even though he does not need an introduction to many of you. Professor Reeves, as has already been stated, had his education in England and he obtained a postgraduate degree in geophysics and a PhD in geophysics. But unlike the other youngsters, immediately he jumped into the field and moved to the very cold continent of Canada. There, straight away, he went to Botswana to conduct maybe one of the very first nationwide gravity surveys. I don't want to go into most of it because all of this has been given in his CVs, and some of you will be, I'm sure, have read it or have gone through and have an opportunity to go through it again. What I vividly remember is Colin's travel in 1983 from Canada to Delft, the Netherlands, to attend an interview for the post of Professor of Geophysics, which was newly created in ITC. Colin by then already had an impeccable academic record, had published practically in every journal around the world, including Nature. Some of us only hear about it. He has already published more than one paper in Nature, and he was the obvious choice for the professor. And I was fortunate to be his colleague for a few months till 1984. By then, I returned to India. But we continued our friendship and we continued our contacts. What ITC, just for the information, I want to tell you, draw students from all over the world, mostly from the developing countries, mostly from Asia and Africa. And all these students were so fortunate that Colin molded them, their lives, and then made them progress in their careers. Some of them occupy extremely high positions in most of these countries, and most of them, of course, have already superannuated too. Fortunate to obtain your degrees, both postgraduate and PhD. I'm sure Dr. Sahu must be hearing it here, under the guidance of Professor Reeves. But what I really cherish is I would like to introduce Professor Colin Reeves as a friend of Indian geoscientists. His contribution to the Indian geosciences is second to none. He traveled to India any number of times, and he advised scientists in various national organizations like NGRI, AMD, GSI, ONGC, NIO, Reliance, and so on, and lectured in various universities, even to the school-going children. One such occasion which warrants a mention was he acting as a convener for a workshop on airborne geophysics, which preceded the second international seminar in 1996, November 1996. Immediately after that, I just want to show, we organized so many workshops, but within a period of 1 year, this is what he brought out. A textbook on airborne geophysics, one of its kind at that time in the world. And this book was a joint publication by AEG and ITC and was released in Toronto, Exploration 1997. That means within a year, the book on net, it was circulated, articles were got, and articles from all over the world which were presented in the workshop were brought out in the form of a book. But what is more interesting and beneficial to India was Colin went on to submit a project to Netherlands government for funding to strengthen digital methods in geoscientific institutions in India. Against very heavy odds, he got $1.6 million grant for the project, and overcoming various obstacles and difficulties, the project was housed in the Geological Survey of India. It is at this stage I wish to pay tribute to Sri Krishnanunni, but for his wise counsel and hard work wherein he stayed in Delhi for weeks together to prepare the background material for the project would not have been housed in the Geological Survey of India. Anyway, with Sri EVR Parthasarathi as the project manager, myself as the resident project coordinator of ITC, the project was a great success. Under the project, 25 people went to ITC as training of trainers, not at free, which was free. And these 25 people, when they came back, they trained over 100 people, over 1,000 people from various geological organizations in and around India in the digital methods in geosciences. That's the contribution which Professor Colin Reeves has done. And the institute, Colin, you'll be happy to know, the institute is strong, is going on, and next time when you are here, I'm sure we would like to felicitate you there. I don't want to take any more of your time. I have already taken more than what is needed, except to say that it's not only in India. Colin has set up similar institutions, similar facilities all over the world, and some of them are still functioning. He is a sought after speaker in any international seminar, and he convened a number of seminars himself. With these few words, I, on all your behalf, I request Professor Reeves to deliver this third Krishnanunni Memorial invited lecture. Professor Colin Reeves, please.
Thank you, Sri Damurti, for that kind introduction. Thanks also to the chairman. Can you all hear me? Yes, okay, then I go ahead. Let me say first of all that I find this a great honor and to deliver this lecture, and a great pleasure to be amongst so many of my friends in India once again, albeit from a distance, thanks to this conference technology. Perhaps one day we can meet again in person. Now, let me share my screen with you. Is that? Oh, no, no. Okay. Can you see the screen now? Is my title slide visible? Hello.
Yeah, it's perfect, Colin. Go ahead.
Yes.
Okay.
Yes.
Fine.
We are seeing.
Okay. Excellent. Then let me start by making some introduction. The title of the talk is How India Parted Company from Gondwana, and I wanted to start with some historical background because I think for the occasion this is most relevant. So I want to show you first of all this picture, which was taken in July of 1957, and it shows the Indian Prime Minister Pandit Nehru on an early visit that he paid to ITC in Delft in July 1957. And here you see he is being hosted by Professor Willem Schermerhorn, who was the founder of ITC and literally moved heaven and earth to set the institute up in 1950. And the initials, people always ask me, what do the initials ITC stand for? Well, originally it was the International Training Center for Aerial Survey, and it has undergone many changes of name subsequently, but the initials ITC have survived. And the particular relevance for the present meeting is the fact that in the years 1969 to 71, Sri Krishnanunni studied in this very building that you see in the photograph and obtained his MSc in photogeology. And in a way, at the end of my talk, I'm going to come back to this idea because the work that I'm describing to you, I think is really a variation on the theme of photogeology, because as you will see, I've been trying to understand how the oceans were created through studying what they look like in various images. So let's move on. Here's an image of Gondwana that you will find very easily on Wikipedia, and it is a South Polar view. And most people these days, particularly I would say people in secondary school, will all tell you a few things. The southern continents of today were once part of a united supercontinent called Gondwana. And towards the end of the Paleozoic era, about 300 million years ago, Gondwana was close to the southern geographic pole and was largely ice covered, a bit in the way that Antarctica is at the moment, we must imagine. And finally, the third point, India escaped from the rest of Gondwana at some stage and moved rapidly northwards in the Mesozoic and Cenozoic times, eventually colliding with Asia with the formation of the Himalaya. Now, I'm going to be talking today mostly about the earlier part of this process, And here are a number of topics that I want to address. And starting off with the concept, what is the correct fit of the Gondwana fragments? Now, back in 1988, this geological map of Gondwana was published by Martin de Wit and a team of co-workers based mostly in South Africa, but with contributions from many other parts of the world. And wherever you travel, you find copies of this map on the walls of geological institutes the world over. Unfortunately, the map is now more than 40 years old. It predates all the wonderful imagery we now have of the world's ocean floors. And when I first saw this map, my interest was fired because I felt that this map was a great step forward. It set the pace in many new ways, but philosophically, there were some difficulties for me because, not least, we could see these gaps between the continents in this free assembly. And in the days before we knew what the ocean floors looked like so well, philosophically, you had to say, well, these can't really have been gaps. There must have been some form of Earth's crust filling these gaps. And then, if that is the case, what became of it and where is it now? And secondly, there's been quite a lot of important work recently measuring marine magnetic anomalies, which of course give us some timing on the events of Gondwana's splitting up. And in particular, perhaps the most relevant piece of work has been in this region here, between Mozambique in Africa and Dronning Maudland in Antarctica. And I want to start by talking about the optimal fit that we should adopt for these two parts of Gondwana. Africa and Antarctica are the two biggest fragments, and if we can get those right, then we should in turn get the smaller fragments into their correct position. Now here's another map that's even slightly older. This is more than 50 years ago. Smith and Hallam published in Nature a paper entitled The Fit of the Southern Continents. What they used essentially was an extension of the Bullard computerized fit methods that were applied to the Atlantic margins. And this was the result of that study that was published in Nature in 1970. And this has stood the test of time in many ways. West Gondwana, their fit is not so different from what people would advocate today. The same is true for East Gondwana, but then somewhere in between we have a discrepancy, because where Smith and Hallam fitted Sri Lanka into this concave dip in the Antarctic margin, in fact, it is this convex part of the coast of Mozambique that should fit there. So here we have a mismatch. And unfortunately, for many reasons, I guess because the correct version hasn't been published well enough yet, you still see this incorrect fit repeated in many publications even to this day. Let me try to convince you of the evidence that supports this fit. Here we have two images of from the world gravity coverage. And on Africa, we see this arcuate feature off the coast of Mozambique. And at the same scale, we see the same feature off Antarctica. And if we see these in their global context, we have Mozambique here, We have Antarctica down here. And although they're now separated by a distance of 6,000 kilometers, this is really what global tectonics is all about. Continents travel large distances, but the footprints they leave behind are often well preserved and allow us to interpret the means by which they made these enormous journeys over periods of geological time. Jumping somewhat to the end of the story, here is what is known as a flow line that connects these two points, one in Africa, the other in Antarctica, symmetrical about the Southwest Indian Ridge here. And as you will know, as oceans spread from this early example from the North Atlantic Ocean, magnetic stripes are frozen into the newly formed crust. So is it the world over. And here is a map showing all the magnetic anomalies picked along that 6,000 kilometer track. A few things to notice. We've got in blue the latest observations from Müller and Jocat that were published just 2 years ago, both in the sea off Mozambique and in the sea off Antarctica. And most important, well, these show that the spreading apart goes on to this day. But most important for what I'm going to be talking about is the fact that we've got this Cretaceous quiet zone from about 121 to 83 million years ago, in which we don't have any of these ocean floor stripes. So we don't have the best type of data for defining the positions of continents at bygone times. So here is what I support as the best present reassembly of the Gondwana fragments. We've now got this error corrected here, and now we've got Sri Lanka nestling into the small space that exists between India and Antarctica, with the Napier complex in Antarctica nestling into this angle in the east coast of India. So we've got this piece right, but it's a very important piece of the puzzle, as I will show you later on. The next two questions I want to address can hardly be separated from each other. If we want to describe the outline of a continent, what should we use to define that outline? And once we've defined it, how close should it be to the outline of the conjugate continent? And neither of these questions are easily answered. To illustrate the point, I'll use the current reassembly, and this has been stable with me and the team from IGCP 628 now for a number of years. And here in green, we see the coastlines of the southern continents in that reassembly. But as geologists, we all know that coastlines come and go as sea levels rise and fall. So they're only geological margins insofar as they limit the extent that the field geologist with a hammer and a compass can physically see rocks on the land surface. The early work of Smith and Bullard and others used bathymetric contours to help define the fit. But I would argue now that we've got global gravity data, it's the gravity anomalies around the margins that are the more reliable markers of the continental edges. This is the same reassembly, but now in purple you see my interpretation of these so-called gravity margins. In support of that, perhaps something that's more familiar to people who've worked with continental geology. I'm adding this layer, and this in pink now is areas that I describe as Precambrian, where the Precambrian rocks are either outcropping or are covered only by a thin veneer of younger sediments. And where they're outcropping, in general, you can say that they are mapped conventionally. Where they're only thinly covered, their anomaly patterns stand out clearly on aeromagnetic surveys, which, as you know from the introduction, is one of the techniques that I've spent the larger part of my career working on. Let's bring this into an Indian context. Here is a global gravity image. There are several of these now in circulation from Earth orbiting satellites. This is not even the most recent, but it serves to illustrate my point. This is from the Danish National Space Center in 2009. I think we can all recognize the outline of India from this image, but let's add approximately the coastline here in white.
Sharing.
All right.
We are sharing. Maybe just leave this so we can see that we are still connected.
Sorry?
Leave this the way it is and just use that so we can see that they are connected.
Okay, right. Okay, hello again. Can you hear me now? We've done something that has turned the noise off, so I will back up a few slides and try again.
We can hear you, sir.
Let me pick up again from this point. I hope then you haven't missed too much. What I've been trying to do is to prepare not only the situation at the start of disruption, but a continuous series of images from that start through, not to the present day, because I think the more recent past is well defined, but the challenge is to get from the start of disruption to the first of the anomalies of the C series about 84 million years ago. So here is a summary of the geological timescale through the Phanerozoic. Gondwana was consolidated very early on in the Cambrian and went through as an entity right up until the start of the Jurassic. And then we have the onset of disruption, an acceleration of the disruption at about the time of the Jurassic Cretaceous boundary. And then around about 120 million years ago, we get the start of the Cretaceous quiet zone. So for a while, we have absolutely no time control, but we have good ocean floor imagery that should allow us to make a smooth interpolation. So the period I've been concentrating on is this one, but relatively little happens during the Jurassic. And from the end of the Cretaceous quiet zone, we've got good control over the way things evolved. And to illustrate this point, let me show you a reconstruction at this time, where we have West Gondwana virtually intact and East Gondwana virtually intact, and a relatively modest amount of disruption between the two. If we move ahead to the end of the quiet zone, you can recognize now very easily all the southern continents. and you can see a well-established series of mid-ocean ridges separating them in a way something like this. And the work has been around making this happen in a way that the oceans only grow. It is unusual for a growing ocean to stop, and it's almost unknown for it to go into reverse. So making that rule work for all these different margins simultaneously is quite a challenge. You can liken it to the fact that if you draw a straight line between 2 points, that's dead easy. If you want to draw a straight line through 3 points, you have to start making some decisions as to what is credible, what is slightly adjustable, and what is plainly not to be believed. Now, this task is difficult, but I would argue now that the ocean floor data is so good that if you do this carefully and with a lot of discipline, the data actually forces you into a corner, which we assume is the correct answer, or as close as we can get to it. So let me illustrate the result by looking at by way of example, to the tectonic evolution of the east coast of India. Here we've got the geology of India, less the Cenozoic cover, together with the geology of Antarctica, and the fit requires a fairly narrow strip. In this case, it's about 75 kilometers wide that follows this arcuate shape. It's probably the original line of rifting, which in turn probably followed closely the weaknesses of the Eastern Ghats mobile belt. And what I've done in this illustration is to outline an area of crust that fills this gap, and that area I've attached to both coastlines so that as we move them apart, we get an idea of what happens to the crust as it's stretched and extended. Here's the fit. Here, just 3 or 4 million years into disruption, we see already that the crust is thinned to half thickness because these two areas of crust are now no longer overlapping. So what was originally full thickness crust is now reduced to half thickness. And that happens relatively quickly along this arm where the separation is normal to the spreading. And here, south of the Krishna Godavari Delta, we've got more of a strike slip, oblique rifting, which means that it takes a while longer for the two parts of the extended crust to completely separate and get into the growth of new ocean. Just let you see that once again so that you see something about the effects of the geometry of the rifts and the extension that goes on. Taking a slightly more distant view now, this is at time M0, the youngest of the M series anomalies. And a few things I want to mention here. We're getting regular ocean growth just here, but we've got magnetic anomalies over here that define the relative position of Antarctica with respect to Africa. We've got magnetic anomalies up here that tell us where Madagascar is with respect to Africa. So it follows that we have this gap between Madagascar and Antarctica quite well defined. And you see here that although we've got quite a bit of growth going on here, the ocean tapers to the west, and there's very little extra space in here than there was in the reassembly. And this is one of the arguments in favor of the reassembly being tight, because if the assembly is much looser than we had it, then there's no longer space for both India and Sri Lanka between Madagascar and Antarctica at this time. So I'll take you through a series of images now that try to explain that in a little more detail. We've got, this is at 124 million. I'll go in steps of 4 million years. And there are magnetic anomalies here off Australia. We don't really know precisely the outline of this, I suppose you could call Tibet, the piece of Greater India that has disappeared into the Himalaya. But this outline fits the reassembly rather well. And we've got magnetic anomalies in here that define the speed of ocean opening off Western Australia. And that goes on. We get, in fact, strike slip on this prominent fault feature off Western Australia. We get initially very little movement between India and Madagascar. Eventually, the mid-ocean ridge in here dies out and jumps to much nearer the coast with India. Then we get the onset of strike slip between India and Madagascar. And maybe for a while there's a role in here for the Kurduwadi lineament, because the model has pure strike slip on this fault line off the northeast coast of Madagascar. All the while we've got regular ocean growth going on down here. And at a certain moment, around about 90 million years ago, we get a change of things, an abrupt change. India starts moving off to the northeast. Let me run that backwards, because I want you to watch in here the way in which the fracture zones off Sri Lanka telescope so well into those recorded off Antarctica. This tells us a number of things, because by now Madagascar is at rest as part of the African plate, so we know exactly where it was. We know where India and Sri Lanka must be. Sri Lanka is now part of the Indian plate, and the fracture zones offshore are now confined to matching those off Antarctica. And to make that happen, we're still not able to have much of a gap between Madagascar and India. So we are confined by the data to accept this kind of picture as we move through towards the moment of takeoff, which is around about 88 million years ago. I just let you see the whole story a little bit more in a global perspective. Here is India, fairly centrally placed within reassembled Gondwana. We've got a huge complex belt of geology on the southern margin. We've got the Tethys Ocean on the northern margin. And then we get the onset of disruption running down the length of the east coast of Africa and into this complex belt of orogeny to the south. And round about 155 million years ago, the sense of spreading changes. It's now possible for East Gondwana to become a strike slip, or to take on a strike slip relationship against Africa. And that's exactly what it does. It's almost as though it was waiting for that to be possible. And on till the end of the Jurassic, we get the outbreak of the Kerguelen plume, and we then have the first triple junction between Australia, Antarctica, and India. And because India is confined at its southern tip, the only response that India can make is to pivot between these two large fault zones, a bit like this. The ridge here reorganizes, comes much closer to the coast of India, and then India takes off. So this is the point that we should switch our attention to what happened on the west coast. Am I going backwards?
Backwards, yes.
Sorry, I'm going backwards for the moment. Here, thank you. Here we are. We're back at 120 for the time being, so that you can follow this this again. Maybe there's some early rifting at this time between India and Madagascar, but there is a long period in which I think there is a very complicated piece of new crust that's being grown in here. It's extended Precambrian crust, but probably not very much of it. There's maybe quite a lot of volcanism. For a long time, southern India is sitting above the point where the Marian hotspot is going to break out down here. And so we get some magmatism, some emplacement of magma in here. And eventually, with the takeoff of India, there's ambivalence as to whether the main active ridge is close to the Indian coast or close to the Madagascar coast. This is not an unusual situation, and at first it looks as though the mid-ocean ridge immediately east of Madagascar is the dominant one. There is some spreading over here. The Lakshmi Ridge will be a relic of this activity, but then we see the growth of the Mascarene Basin becomes predominant until about 62 million years, when that growth dies. And for a while, this enormous Vishnu fracture zone becomes a real transcurrent fault with an offset of about 1,700 kilometers. And the active ridge is once again quite close to the east coast of India, and no doubt influenced in some ways by the Reunion hotspot, which has started out producing the Deccan traps and goes on to leave its trail across the whole Indian Ocean. So I've given you a lot to take in, but I just want to end and summarize in a way, because I think if you're interested in studies of this sort, nothing short of a global view really can help you understand what's going on. And in this respect, I feel somewhat restricted myself, because I've only looked at half the world. I've not been integrating this study with what's been going on in the other hemisphere, but I've learned quite a bit across along the way. I just want to remind you what a wealth of detail exists in these ocean floor images, and this is a repeat of the situation I've seen time and again with the national aeromagnetic surveys. There's probably 10 or 100 times more information in the data than is ever interpreted. It's just the same with these beautiful images we have of the ocean floor, and that is why I want to end on the note that really it's the photogeology of oceans that is what this study is all about. There's so much information there now. More will undoubtedly come in, but as is always the case in the earth sciences, if we wait to do our interpretation until all the data has been collected from all possible sources, we'll never make an interpretation. And the smart money, in my estimation, goes on making the most of whatever data is available and coming out with the most credible solution. I'll finish on a note that I think is an important one, and I presented this final animation just a few weeks ago at a meeting at the Geological Society in London. And I think well, I hope the animation speaks for itself. Unlike a lot of workers, I've tried my best to model not only the position of the continents, but the positions of all the mid-ocean ridges that separate them. And here is an animation where I've simply deleted the continents, and what we're looking at is how the mid-ocean ridge system grows from the start of the Jurassic until the present day. And if you look at this in the context of the constellation of mantle plumes that are known across this hemisphere, you're rapidly forced, I think, to the conclusion that the continental drift is not so much about continents drifting, it's about these mid-ocean ridges staying in the same place. I'm sure many in the audience are following the progress of India. It does what we all know that it does. It moves rapidly north as time goes on, but that's mainly because down here, further south, we've got a whole series of mantle plumes that are all driving the machinery of global tectonics, pushing India in the same direction. So if you want to understand the evolution of our planet, I recommend thinking of the continents, the familiar continents and their geology, simply as passengers on larger tectonic plates that are under the influence of forces that not only drive them apart, but, and this is the half of the story that I've totally neglected, there are undoubtedly other forces that suck the plates back into the Earth's mantle in the fullness of time. So I want to end by thanking a whole lot of people who've contributed to this work in various ways. I won't mention them all. You can see the list here, but I would like to particularly thank Professor Sridhar Murthy, because it is through his kindness and cooperation and perseverance that I've been able to enjoy associations with India that go back almost 40 years now. I've got a website which goes into more details on quite a few of the things I've been talking about. I'm very happy for individuals to contact me at my email address, which is here. And it only remains really for me to thank you for your kind attention, and apologize that we had a lapse in the technology somewhere halfway. Thank you.
I think, Colin, with your permission, can I invite questions?
Of course, of course.
Yeah.
I will stop sharing for the moment, and then you can see me again, I hope. Yes, there I am. I'm back. Okay, yes, I see me again now in the corner of the screen. I'm happy to take questions.
NC Pant, would you like to ask something?
Yeah, sure. Professor Reeves, it was very nice listening to an excellent talk, actually. I do some work in Antarctica, and I'm also working in Karakoram, that is Eastern Ladakh. And I see this approach of course, looking at essentially from the ocean photography context, and then looking at, so I'm working on the continental context.
Mm-hmm.
So some of the new data which I find from Eastern Karakoram, Eastern Ladakh, let us say, has some detrital data in metamorphic rocks. In metamorphic rocks, the zircon is paleo to Mesoarchean, very old zircon, which is not very easy to relate till we don't relate a part of Tibet to Australia. And that is what I see from some of the reconstructions which, uh, which you have shown as separation of the Indo-Australo-Antarctic triple point. And it seems that the Tibet or parts of Tibet continue or contain some parts of Australia, past Australia, at least the sourcing from Australia. And that very well matches with what you have what you have described as the motion of the Indian plate and loss of the greater Indian landmass. Okay.
Thank you for the question. I appreciate that. I'm afraid we've got the squeaky wheelbarrow has come back again at this
Sure.
this side. But yeah, I don't know nearly as much as you do about the geology of Antarctica or the east coast of India or Australia for that matter. But one thing that occurs to me through all this work is that I think perhaps almost a bit naively we expected the geology to continue from one continent to another across the join. Perhaps it would if we could only reconstruct the rifted zone more precisely, but over a distance that is often 100 or 120 kilometers. It's often very difficult to correlate geology, and very often the ruptures between continents follow lines of weakness that are themselves old discontinuities. So I without wanting to discourage people who are trying to map the geology, I'm not too encouraged by how far we're going to get trying to match geology across continental margins. It seems to me to be one of the less successful approaches so far.
Just one more.
Of course.
Yeah, we generated, or part of a group, we generated some data over Princess Elizabeth Land in Antarctica, which is actually the domain where possibly the triple point of the India, Australia, Antarctica is located. Now, it's very disturbing, this noise. Somebody's mic is not switched off. It's causing a lot of.
You've got it too. Okay. So well, I'm trying my best.
Yeah. So the geophysical data, magnetic data especially, showed a very strong 1600 nanotesla anomaly inside, about 400 kilometer inside Antarctica, which we interpreted as the possible suture linking India, Australia, Antarctica, or coming to that. Now, the question which I wanted to ask was, how good, if one looks at the such kind of continental triple points which separated in time or previously, how good is the geophysical data to register this?
Well, I'm all in favor of as much geophysical data as possible. In my experience, there's never enough data, and that is ultimately the problem that we have to contend with. And I think particularly when you get down to the scale of a few tens of kilometers, that area of the triple point between Australia, Antarctica, and India is one that underwent a very complex breakup. You've got extra fragments there, like the Natural East Plateau, and maybe even a Precambrian part of Kerguelen, that led to a very complex rifting history that I've only skated over very lightly. I guess to keep things within manageable proportions, I try to focus on places where the rifting history is quite straightforward. And even when you zoom into the South Atlantic margins, which is sort of classical plate tectonics, when you get down to field scale, the story is much, much more complicated. And I suppose life wasn't meant to be easy, but it's still a challenge to go from the scale that I'm working at to the scale of field observations. But I think we've got to try. And if you want, if you've got publications you can send me on the work you've done, I'd be very interested to read them.
If you will permit, I will send those and interact further without the noise, of course.
Please do. I'll be pleased to hear from you.
Most welcome, Mr. Pant. Anupendra Gupta, you have raised your hand. Do you like to ask? Please unmute. Mr. Gupta, you have to first unmute. First unmute, please.
What I was telling, am I audible now?
Yes.
Am I
yes,
audible?
Yes.
So in my case also, to a great extent, being a geologist and that too Precambrian geologist, my questions are also centered to the passengers who are sitting on your scale of plates. Passenger means the continental components. So my question is about the eastern coast of India, where we have a mobile belt. We call it Eastern Ghat Mobile Belt, representing high temperature granulite rocks along the eastern coast of India. And there have been many hypotheses about its match with the Eastern Australian continent, because we find that this mobile belt has got impression of crustal segments coming and docking with it from the Cambrian, from Archean time, and also getting a name of mobile belt, which is much younger to that. So now, and there is another within this, also on the northern side, there is a segment, triangular segment, which is now people are recognizing this as suspect terrains. That means a crustal fragment has come from somewhere. We do not know. We are not able to really designate them with any continent. It's not matching with the Indian crust. It's far away, as you said, with the Australia. So now here these things are live points of our reckoning in the continental geology. Now, whether these could be some of your studies, whether eastern coast of India has got interactions with away, that is Australian, this thing, because there are some matches when you close. So that is my question. Of course, your scale of study is much larger than what I was mentioning, a continental scale. Do you
Yeah,
have
well,
any magnetic or gravity or any geophysical signature along eastern coast of India?
yeah, no, thank you for the question. I think my answer is going to be much the same as my answer to the previous question. That I wish I had the data. I wish I had the detail, but I firmly believe that we have to start looking at whole continents and then progressively focus down to the more detailed items. And unfortunately, so many of them are hidden from view. I was learning at this meeting in London recently that even where the margins of South America and Africa have been studied in great detail with high-resolution seismic surveys, there are still so many complications that that make the issue of exactly how they fit together anything but straightforward.
My point is that if your group keeps in view separately these problems of continental crust problems that we are facing, who have been working on the continent. Now, this is fascinating what you describe, that it's more important to look at the ocean, which is spreading and which is also closing in. So these are the things to be understood, and geophysics is the main tool for this. So that's very fascinating, and thank you very much for giving this perspective.
Thank you,
Thank
Dr.
you. And I think the most important of all is that we keep working together and talking to each other, because only this way do we deepen understanding.
Right.
May I request Dr. Shailesh Naik ji to say something, please, before Mr. Pasadi proposes a vote of thanks.
No, thank you very much.
Dr. Naik, you have to unmute. Dr. Naik, you have to unmute.
Thank you very much, Professor, for your very inspiring talk, and I'm sure that we all have been a little wiser now after this talk, and thank you very much, and hope to be in touch with you in coming years. Thank you very much. Thank you.
My pleasure. Nice to see your face.
Those who want to raise a question, will you please send a mail to Colin, and I assure you that you will get a reply very soon, in spite of the fact that he still gets hundreds of mails every day. With your permission, may I now request the Secretary of the Sri Krishnanunni Memorial Committee, Sri EVR Parsardi, to propose a formal vote of thanks.
Friends, it's my present duty to propose a vote of thanks. First, to Professor Colin Reeves, who has agreed to our request to deliver today's talk. Not only that, and he has adjusted to our timings. That is about 6 o'clock when I told him, he readily agreed for that. And then timing, today date also he has agreed. Not only that, he has given us such an informative and a lecture. I think it opens new frontiers for our people to carry out the research. He has given a broad outline. I profusely thank him for his effort. And then my request to him is, if possible, share his slides with our society, KMCT. You can send it to me or Professor Sridhar Murthy, if possible. Well, I thank Professor Dr. Shailesh Naik, our president, for having ably conducted these proceedings. And also to Professor Sridhar Murthy, who has introduced Professor Reeves. And then I think when Sridhar Murthy says he has four decades of contact with him, I can claim that I have a contact with Colin Reeves for more than 2.5 decades. So I was knowing him from late 90s onwards. And it's a great pleasure to have him today in our midst. And I, I, I thank all the participants, not only from Krishnanunni Memorial Trust, from many other organizations who have joined today's meeting. My particular thanks to the family members of Krishnanunni who have joined this fund, this talk, and then participated fully. And I thank again, this is the third of our series of Krishnanunni Memorial Lectures, and we are waiting for the next series of next lecture in future. Thank you very much. Thank you.
We close the meeting.
Nice to see Professor Sridhar Murthy after a long gap.
Yeah, probably he's one of the closest person who's living close to my house.
Yes. Very nice. It's after a long gap. A few years.
I'll catch up, Dr. Chetty. I'll call on you one of these days.
Sure, please. We will meet.
Nice to see.
Nice to see you in such a usual mood and spirits. I saw you.
Yeah, I just want to say something about Dr. Gauri Sivarajan here, please. Dr. Gauri Sivarajan. She was there. In fact, her camera is on, but maybe Parsadi Garu, if you can send the number, I'll call her separately, please. I'm so happy that Dr. Gauri Sivarajan has come here and she's on the screen. She's a medical, she's a doctor by profession and younger sister of Mr. Krishnanunni. Yeah. Goodbye for now, please, to everyone.
Thank you.
Bye-bye.
Thank you.